Alright, we're going to work problem 9.8 from the Thermodynamics textbook. It refers to problem 9.7, but it has you using the specific heat at 520 degrees Rankine, and it is a cold air standard. A really good habit to get into is starting off with a PV diagram. This one here shows our problem. The pressure along this line here is 14.2 pounds force per inch squared, because it was part of the given from problem 9.7. The first step we're going to try and do is, we have the information for state 1 right here, but we need some of it for state 2. So if we're solving for the state 2 temperature, we can use equation 6.44 because it's an ideal gas, and being that it's isentropic, it makes it pretty easy for us. So that equation is V1 over V2 to the K minus 1 multiplied by T1. If we plug in what we know, we have the compression ratio, so we have 8 to the 1.4 is 0.1 minus 1 times the initial temperature, 520 degrees Rankine. If you plug all that into your calculator, it should come out equaling 1197.1 degrees Rankine. To move forward, we can use an energy balance. The change in energy equals the heat in minus the work out, and there is no heat leaving, or no work being done between states 2 and 3. However, we do know that there is a change in temperature because it was given right up here in the problem. So we can plug in the mass times here equals 0.9 BTU. And we also know that, sorry, the BTU there, it's pretty bad. We also know that the heat in is equal to mass times the specific pressure, or excuse me, specific temperature. So the final equation we can use is going to be the temperature at state 3 equals the heat addition from states 2 to 3 over mass times specific volume plus temperature at state 2. When we plug in the information we have for this, we get 0.9 over 0.015 pounds times 0.171, and then you add the temperature we solved for up here, 1197.1 degrees Rankine. This all ends up solving out to 4705.9 degrees Rankine, which is temperature of state 3. State 3 has the highest temperature as well as highest pressure. So part A, temperature at 3 equals 4705.9, which we need to round it off. Degrees Rankine. Okay, I cleared out some of the other stuff to make some room. Now solving for the pressure at state 2, we can use equation 6.43 from the tables, or the equation sheets, and we can modify it slightly so that we're solving for the pressure at state 2. When we plug in our information that we already have, we have the temperature from state 2 over the pressure, or excuse me, over the temperature at state 1, 0.401 minus 1, and then we multiply that by the pressure from state 1, which was 14.2. When we solve it all out in our calculator, we get 261.5 pounds force per inch squared. Now similarly, we need the pressure for state 3, which we can use the fact that it's an ideal gas that comes from the fact that we have T over 3, T over 2 is equal to T over 3 and T over 2. So kind of backwards there. But when we plug in our known values, we have the pressure or the temperatures that we've solved for. And we'll multiply that by the pressure that we just now solved for also, 261.5. And that'll give us a final value of 1027.98. Again, the units for this are going to be pound force per inch squared, and then rounding it off to a cleaner number of 1028 pounds force per inch squared. It's best when doing your calculations though to use the more complete answer and then just save these ones here for everything else. Alright, sorry to keep things jumping around on you. I cleared off the answers we've solved for off to the side. Now working on part 3, we need the thermal efficiency. In your equation sheets, if you go to equations 9.8 and 9.1, we can modify them to start off with this part here is 9.8, equation 9.8, excuse me. And then we know R is equal to the compression ratio. Sorry, had a mind blank there. So when we plug in our values, we have 1 over compression ratio of 8. We plug in the K value in the tables over 1, we get 0.5656. But since we are doing the efficiency, it is a percent, so we have 56.56%. Now part D is a little bit different. If you read the problem, it's asking for the effects of varying compression ratios and plot the quantities calculated in parts A through C for comparison ratios ranging from 2 to 12. I wasn't going to try and tackle that by hand on here, so what I did is I made a second page here where we have the code I plugged into Interactive Thermodynamics, or the IT program, which generated plots that looked much like these over here. I'm not the best artist, so these are the rough ideas. This first one here, you have the max temperature versus the varying compression ratios. So as you can see, it gradually inclines, it starts off a little steeper and then smooths out the higher the ratio. For part 2, this is over here, it's the highest pressure, also state 3. It's a lot more linear through the increase because compression ratios and pressures are a lot more hand in hand than the temperature will be. And then this third one down here is with the varying thermal efficiencies. It is much more of a quadratic, the way it increases more rapidly at the beginning, and then it does steady out much quicker than the others. So I hope this helps you with problem 9.8.